In this video, we'll start discussing applications of matrices and determinants, and our first one is Cramer's rule. Now, in the last section, we noted that the solution to the system a1x plus b1y equals c1 and a2x plus b2y equals c2, where a1, b1, c1, a2, b2, and c2 are constants, is always ends up being this form. This actually, and the important thing to note here is that really what you have is, this is really, this right here, if you pay attention to this, is really the determinant of C1, C2, B1, B2 over the determinant of A1, B1, A2, B2. And this is really the determinant of A1, A2, B1, B2, or no, C1, C2, sorry. 1, C2 over the determinant of A1, B1, A2, B2. Okay? So what's interesting is this even works for a system with 3 equations and 3 unknowns. Namely, for example, if we had this as our system, if we wanted to solve for x3, then we would have the determinant of a3 over the determinant of a. So just as we replaced here, we replaced the first column with our constants by when we were solving for the first variable x. When we solve for the second variable y, we replace the second row. And so here, since we're solving for x3, we would solve out for, we would replace the third row. And that's why we have the b's there that replace. Okay? So in general, if we continue this notation, we have what's called Cramer's rule. If a system of n equations and n variables has a coefficient matrix, then the solution is the following. Namely, we get exactly what we got before. Here we're replacing the first, we'll replace the first column of the determinant of A instead with our constants, which would be some b1 through bn. And then this one, then we would do the second column, and the third column, and all the way up to the nth column. Where the ith column, as I said, of AI is the column of constants in the system. If the determinant of A is 0, then the system has a non-unique solution. And this is basically what we saw last time as well when we talked about solving systems of equations, or not last time, back in 8.3 when we used inverses. So for example, let's try solving a system out using Cramer's rule. So here first, it's helpful to write out all of our coefficient matrices. So we would have what? Well, here we basically have the matrix. Let's write down the augmented matrix: 4, -2, 3, -5, 10, 11. And so here we have that A is going to be 4, -2, 3, -5. And then to find A1 and A2, we just substitute in the first column with the constants, so 10, 11, but otherwise leave it the same. And to find A2, we do the second column, so 10, 11, and otherwise unchanged from A. All right? Which means x, being the first variable, will be the determinant of A1 over the determinant of A, which is what? It's going to be 4, -5. Yeah. So 4 times, that's going to be 4, 3, no, 10, 11, sorry, I looked at the wrong one. 10, 11, -2, -5, over 4, 3, -2, -5. So we have -50 minus, plus 22, because minus -22, so plus 22, over -20 minus -6, so plus 6, which gives us negative 28 over negative 14, which will be 2. Similarly, y is a2 over a. We already calculated a out. That's the nice thing. So we calculate it to be what? Negative 14. The determinant of a2 is 4, 3, 10, 11. And so we have 44 minus 30 over negative 14. 44 minus 13 is 14, so we'll get negative 1. And thus we have our solution, which is 2, negative 1. If you want, you could always go ahead and check this as well. And now it's your turn to try an example, so go ahead and use Cramer's rule to solve the following system of equations. On the count of 3, I'll reveal the solution. 1, 2, 3. So here we see that we go ahead, and I went ahead and solved out for each of the determinants beforehand. Then I can just plug them in to get my answer of negative 3, 2. Now, one question you may ask is, what's so bad about this? Well, if you try solving this out of absolute a equals 0, first off, in the formulas you'll see that you get 0, so you get a division by 0. But interestingly, in this example, for instance, you would have that. It would be 12 minus 12, which would be 0, right? Absolute of a would equal 3, 2, 6, 4. So the determinant of them would be 12 minus 12, which is 0. And indeed, what we see there is that happens because this row is a multiple of that row. Namely, if I was to do some sort of elimination by multiplying by 2, by negative 2, I would get negative 6x minus 4y equals positive 4. And down here I would still have 6x plus 4y equals 4. That cancels, and so I get 0 equals 8. But that has no solution, as we've seen prior. Namely, this actually helps us see that, oh, well, actually, you would have no solution there. All right? And actually, it could be, all that tells us that there could be a 0 here. There may have been a 0 over here, and if there had been a 0 there, then we still would have had a 0 determinant. But namely, the determinant of a being 0 picks up whether you're going to end up with a 0 over there. So let's do another example. Let's use Cramer's rule to solve the following system. So here, same idea as before. Namely, we have here the augmented matrix negative 1, 2, 3, 2, 0, negative 4, negative 3, 1, 4, and 1, 0, 2. Okay. And here we'll go ahead and calculate the determinant straight off. So determinant of a is just the determinant of negative 1, 2, negative 3, 2, 0, 1, 3, negative 4, 4. Doing that determinant, I'm going to expand along the middle column. So we'll have 2 times the determinant of 2, negative 3, negative 4, 4. Plus, well, that'll be negative, sorry. Forgot about my sign. So negative, because lest we forget, plus, minus, plus, minus, plus, minus, plus, minus, plus. So negative, positive, negative, along there. Which gives us, what? What will that give us? That'll give us, just blanked. 2, 0, that'll give us negative 2 plus 0 minus 1 times the determinant of negative 1, 2, 3, negative 4. And that's going to give us what? Negative 2 times 8 minus negative 12, so 8 minus negative 12, so 8 plus 12, so 20. minus 1 times what? Positive 4 minus 6 is negative 2. So we're going to get positive 40. No. What did I do wrong? Here I did something wrong. What did I get? I get 8. Ah, no. Oh, yeah. Yeah, sorry, I got confused. 8 minus 12 is negative 4. 8 minus 12 is negative 4, yeah. So I get 8 plus 2, so I get 10. Sorry about that. So I get 10 there. Then I have A1. I can calculate similarly A2 and A3 as well. Calculating out A1, you would have, we're replacing the first column by 1, 0, 2. And replacing by this, so 1, 0, 2. So that would be what? Negative 1. Give me a moment. 1, 0. I'm blanking. 1, 0, 2. And then 2, 0, negative 4, negative 3, 1, 4. If you go through and you calculate that determinant, you'll end up with 8. I'm just writing them out at this point. And then a 3. Here, determinant here, again, we go ahead and we write in everything except for the second column. And the second column will replace it with 1, 0, 2, the constants. If we go through and we do that, we'll end up with a negative 15 there. And then finally for a 3, we write it the same as A, except for the last one we replace with the constants. Doing so, you'll end up with negative 16. And by the way, the easiest way to expand is along there. So indeed, you'll get a negative 1 times negative 4 minus 4 is negative 8, but the negative 1 will go positive 8. And then these can move similarly. And so we have x is equal to A1 over A, y is equal to A2 over A, z is equal to A3 over A, which will be 8 over 10, negative 15 over 10, and negative 16 over 10. Simplifying down, we'll end up with 4/5, negative 3/2, and negative 8/5. So those are now our solutions. That is our solution. Now it's your turn to try an example, so go ahead and compute the determinant of, by computing the determinants, go ahead and solve the system of equations. On the count of 3, I'll reveal the solutions. 1, 2, 3. So here I calculate out the determinant of A, determinant of A1, determinant of A2, determinant of A3, and I went ahead and just expanded along the top row for each of them to compute them. And thus, using Cramer's rule, we get x is 2, y is 3, and z is 1. Negative 3, sorry. 2, negative 3, 1. For more practice and using Cramer's rule to solve systems of equations, be sure to see the textbook, page 595. And in our next video, we'll talk about a different application of determinants, which is finding the area of a triangle.